generative model through associative memory.
Thank you. Thank you. Yes, so I want to tell you a little bit about our work on dense associative memories. And dense associative memories are extensions of what is called celebrated Hopfield networks of associative memories. And I also want to apologize up front to some of the people in the audience who might have heard some parts of this talk, but I'm going to talk a lot about some new results, so I promise there will be something new for pretty much everyone. So when we talk about associative memories, the central and essential concept is this notion of the energy landscape. So essentially, you can think about associative memory in the following way. Imagine that you have some nonlinear dynamical system or nonlinear neural network, if we wish, that is described by some time-dependent vector. And that vector evolves in time according to some nonlinear rule. And what is cool about this temporal evolution that there is this scalar quantity that you can define that is called the energy. And the energy is defined in such a way that this nonlinear temporal evolution always leads to the decrease of that energy. So in some sense, you can think about the state of this neural network as this red ball that is located somewhere high up on the energy landscape. And then as the network does the computation, that red ball rolls down the hill. And a good energy landscape in this class of models is typically designed in a way so that it has many local minima. In this cartoon example, you can see 4 local minima that are denoted by xi1 through xi4. And each of those xi's is a very high dimensional vector. So they live in the n-dimensional space. And the terminology here is the following. So these vectors xi are called memories. And this whole kind of dynamical system, it's supposed to model the process of memory retrieval. So you can think about it in the following way, that when we start somewhere high up on the energy landscape, its initial Q. I, for example, show you an image of a strawberry. And then as the ball rolls down the hill along the energy landscape, you kind of recall what the strawberry tastes like or smells like. So in that sense, you can think about this dynamical system as the process of memory retrieval from the synaptic weights of the neural network. And that's how we typically think about this. And the reason why this is called, by the way, associative memory is because the association happens between the initial state where you position that ball at t equals to 0 and the final state where that ball ends up being in the limit t goes to infinity. So the association happens between these two states, and this association happens through a heavily recurrent and nonlinear dynamical system. So that's what is somewhat non-trivial.
Can I ask actually something just to clarify? So you said you want the x's to be local minima. You drew them as global minima. Do you just mean distinct global minima, or maybe you don't care if they're local or global?
Yeah, in some sense, I don't care if they're like the absolute ground state or they're just local minima. For me, I'm always working in the 0 temperature limit for everything except for the last part when I'm going to talk about diffusion. And when we are in the 0 temperature limit, essentially, you just find the local minimum which is closest to where you start. So in that sense, it doesn't really matter. Now, at a slightly deeper level, it actually does matter. So it turns out that a good associative memory would have all the local minima somewhat democratic. So you don't want one local minimum to be much deeper than the rest. So kind of like you want them to be in a certain energy band, and that energy band needs to be sufficiently narrow. So that's what we typically want from these systems.
Do you think when you give it a stimulus to the system, that initial position, you will converge to you think that you will converge to a specific local minimum?
Correct.
There are maybe many local minima associated to that.
Right.
Close.
So again, if we are working in the limit when a temperature is equal to 0, there's no noise, right? We always go down the hill. Then for every point there is a unique local minimum. If we allow a little bit of stochasticity, if we kind of put it on the boundary, if we, for example, initialize the network right here, right? So it can go to the right, it can go to the left. And that could be determined by noise. It can also be determined by external inputs to the system. Like you can introduce some little currents that kind of inject some information. And that could also bias the, where the network would go. But normally, in most of the situations, again, unless we're talking about the very last portion of the talk related to diffusion, it's a zero temperature limit, no noise, everything is deterministic. So you start from the point there is deterministic mapping to the fixed point. Okay, so that's the idea. And now what can we do with this idea? Here I'm going to show you a couple of canonical use cases of this idea. So essentially, imagine that I take some data. Think about the data as images, for example. And I'm going to simply take those RGB values of every pixel. I'm going to flatten them out in the n-dimensional vector, and I'm going to encode them as local minima in this energy landscape. And then I can start with some corrupted state. So I can start with the state where I remove 3/4 of the image. And if I let this associative memory compute, you can see that it can produce the missing parts of that image, right? And another use case, same idea, also idea of removing removing some perturbations. You start with a noisy version of the pattern, and that's what you can see on the right. And if you let the network compute, it can remove the noise and it can recover the correct memory. And essentially, like the core idea that you can see from these little illustrations is the idea of error correction. So essentially, and that's the main functionality of these kinds of associative memories, that they do error correction. So you present an input that is not the exact match to the memory, but it can deviate in some meaningful ways from the final answer. But the network is able to do this error correction. And another thing that I want to briefly mention here, from these two examples, you immediately can see analogies with the two prominent paradigms in the modern generative AI. One paradigm is LLMs and transformers, right? And typically, in that paradigm, what you do something similar to what you see on the left. So you tokenize your data somehow, and then you occlude some of the tokens, and you predict the missing tokens. So you do pattern completion. And in the second example that you can see on the right, it looks a little bit like the diffusion model. So you take the sample, you perturb it with noise, and then your network is tasked with the denoising scenario. And already from this high level, you can see that this idea of associative memories might offer some interesting insights in these two Gen AI frameworks. So let's now try to define this idea in a little bit more mathematical form. So specifically, let me think about the state of the network as a binary variable sigma I. So let's say that I have n of those. So I have this n-dimensional vector, and each element sigma I can be equal to plus or minus 1. So for those of you who are coming from the physics background, it's a little bit like an Ising spin. And essentially what we can do is the following. We can write the energy function using in this form, where Tij is some symmetric matrix. And this symmetric matrix can be computed from the memory vectors. And let's say that someone had given these memory vectors to me. So let's say that I have a collection of memory vectors xi, and these xi's are exactly the same xi's that you can see on the previous slide. So the upper index, which I denote by the Greek letter mu, indicates the identity of the memory. And each of those xi's, I remind you, it's a high-dimensional vector, and the projection of that vector into the embedding space is denoted by this Latin index I and j. So that's how we compute this matrix. And so here, essentially, the setting is the following, that the network has capital N spins, or we can call them neurons. The reason why we sometimes call them neurons, because you can think about sigma I when it is equal to -1 as a silent neuron, and when sigma I is equal to +1, you can think that the neuron is firing an action potential. So there is some amount of biological motivation here. So essentially, there are n of those compute elements, and there are capital K memories in this system. And we can define this energy function using these two formulas. So what people realized back in the 80s is that it's a really nice model of associative memory, but only when the number k is small. So it turns out that if the vectors xi's are random, let's say that we draw patterns at random from a simple distribution when they're equal to plus or minus 1 with equal probability, then statistically we can prove that the largest amount of patterns, of such random patterns that such network can store, scales linearly with the size of the network. So essentially, 0.14 is an interesting coefficient that one can compute analytically. But what is interesting here is this linear scaling relationship with the size of the network.
In the previous slide where you had these nice demonstrations, how many memories were competing with the one that was produced?
Oh, you mean in this little animation?
Yeah.
I forgot, but it's 10-ish. 10-ish and
much lower than this limit, right?
Correct. It's much lower than this limit, but I think like based on the language that you phrased this question, I think you might jump to an incorrect conclusion because you might think that because of that, this network is much below the memory storage capacity, right? Which is incorrect because these memories are correlated. So all these bounds are derived for random memories. Once you start introducing correlations between memories, and images are heavily correlated data, right? So like then they're far from random. All these bounds, they become even more grim. So like it's not like 0.14n. You are lucky if you can store 2 patterns, right? Yeah. So coming back here, so essentially there is this nice theoretical result that the capacity of this network and the largest number of memories that one can write, people call this the capacity. So essentially it scales linearly with the size of the network. Now, it turns out that if you take this idea, which kind of, is a sound mathematical idea, and you say, okay, let's try to build some, meaningful AI applications on top of this idea. It turns out that this theoretical bound becomes extremely annoying when you try to do that. And the reason is the following, that in typical AI applications, the dimensionality of the input space is given. You cannot like play with it. It's like dimension of the images or dimension of your embedding space. So n is given. But given n, you want to store as much information as possible. So you want to have a lot of memories. And it just turns out that this linear scaling relationship is very annoying, and it would break your system pretty much anytime you try to build something non-trivial. For this reason, we started thinking about how can we overcome this annoying linear scaling relationship. And this brings up the idea of dense associative memories. Sometimes people also call them modern Hopfield networks. So the idea here is that you want to modify the structure of this energy function in the following way. You want to introduce higher order couplings between sigmas. So notice that this energy is quadratic in sigma. And of course, again, like for those of us who come from the physics background, we know very well that quadratic systems are relatively simple. Non-quadratic systems are much more complicated. So in order to understand what this formula means, let's rewrite the standard Hopfield network in a slightly different form first. So if I take this definition of the matrix T, plug it in here, and slightly remassage the sums over the memory index and the ambient embedding indices I and j, hopefully you can see that I can rewrite this energy function in this simple form. So essentially I need to take the dot product between the state and each individual memory, and then I square that overlap, and I sum with respect to all the memories, and that's my energy. So the only difference between these old Hopfield networks and the dense associative memory model is that instead of squaring that overlap, I'm going to pass it through some function f. And that function needs to be chosen in a certain way to have certain computational properties. But the kind of conceptual insight here is that this function f needs to grow very rapidly. So it needs to grow like exponentially or like a power law, but it needs to grow much faster than quadratic. So let's kind of define this new model this way, and let's try to play with it a little bit. So imagine, for example, that this function f is chosen like x to the power n, where little n is some integer. Let's say that little n can be equal to 2 or 3 or 5 or 4. And we can try to repeat the same calculation. We can ask how many random memories we can store and retrieve in this network. And it turns out that for this power law, we can now retrieve a power law-like behavior for the number of memories. So it turns out that the capacity scales like size of the network raised to the power n minus 1. And of course, for when little n is equal to 2, we go back to the old Hopfield network, and that's a linear scaling. But if, for example, n is equal to 3, suddenly we have quadratic scaling relationship. And of course, quadratic functions grow way faster than linear, right? And that's a huge already improvement. Moreover, it turns out that we can even plug in more aggressively growing functions like exponents. And if we do that, we can even achieve an exponential memory storage capacity. Yeah, please.
Some other applications where you want to control, like you don't necessarily always want to have tons and tons of potential memories and fixed points, right? Because if you only have a little bit of memory, you're going to have loads of random fixed points which don't necessarily like mean anything semantically. So is there a kind of like, I guess a lower bound and an upper bound, and you can control those through your energy functions? I mean, you kind of know that you've stored maybe approximately at least just the memories you're interested in, or?
Right. So let's think about this. So let's say that I give you a binary string of n bits. What's the total number of configurations that you're 2 to the power n, right? 2 to the power n. So like that's the total number of states. So because we want the system to be error correcting, there needs to be some meaningful basin of attraction around each of those meaningful memories, right? So you cannot go to 2 to the power n. There's clearly some bound, right? Otherwise, every point becomes an attractor, which is not interesting. So if you take a look at this model with an exponent, you can see that the answer is square root of that number, right? So it's square root of 2 to the power n. And of course, square root of the 2 to the power n is a much, much, much smaller number than 2 to the power n, right? And essentially, by simply doing this kind of naive computation, you already can see that each basin of attraction has a substantial volume around it. And it turns out, and there's a very nice series of papers that quantified and measured those sizes of the basins of attraction. And it turns out that for these dense Hopfield networks, the size of the basins of attraction is approximately the same in the high dimensional space as for the quadratic one. So they don't really shrink that much. But again, notice that we are still way below 2 to the power n. So like the problem that you are pointing out, it would arise if we go even higher, right? So it would arise somewhere between this model and when we store every configuration as an attractor. And in some sense, if you think about this, when n is large, square root of 2 to the power n, it's already more than enough for any AI application. So in some sense, it might be an interesting question to investigate, but I would argue that practically it's kind of, it's infeasible to get there.
Mm-hmm. It looks like you want a faster and faster growth, right?
Again, up to a limit, right?
What is the limit? That's the question.
Well, I mean, that's what in some sense connected, this question is connected to the previous one.
You have exponential of an exponential.
You could, but then I have not done the calculation for that kind of function. Of course, we can imagine many functions that are faster than exponential, right? The problem is that these calculations are generally somewhat sophisticated, so they require like a lot of sophisticated mathematics. And I'm sure at some point you can get to that limit when like the whole construction does not make any sense anymore. But the point is that, like for example, if we're in the exponential family, the construction still makes sense because it does error correction, and already you have an exponential number of memories. So like practically speaking, I would argue that we should be somewhere below that bound. We don't even need that. Even that bound is a bit of an overshoot for what we really want from this system.
But it's not completely clear, right? Because this is for like random patterns, right? If the patterns, you said that the patterns are correlated,
yeah,
this number could be much larger.
Smaller.
So, much smaller.
Yeah.
So in practice, presumably what we see is like a lot of it is very, very correlated.
That is
so
correct.
You probably have much lower effective capacity.
You're right. You're right. You're right. And frankly, I always feel that there is not enough discussion and study of this in the literature. I think it's indeed nice to look at correlated patterns and see how these bounds, drop. But the point is, if you take this system and investigate it numerically and give it like very correlated data, like by simply going from n equals 2 to n equals 3, you already solve all the empirical problems. So it's just like, even like you don't even need to go to the exponential family. Like power law already gives such an improvement that pretty much you can solve any task that you can meaningfully think of with just like, without separating those bounds.
So I'm inclined to try to think about a slightly different energy function that allow me to present an arbitrary number of patterns, which would be, for any point in the space, just compute the distance, have the energy be the negative distance to the closest point in your memory, in whatever metric you like, right? So in that sense, you have zeros at any memory, and if you do steepest descent in that geometry, you'll go to the closest point.
Correct.
So, I mean, why not use that energy, say?
You can use that energy. And if you use that energy, you would discover that you can store a very small amount of memories for the following reason. Because once you pack a lot of them, think about it like this. So essentially, let's say that I'm using L2 distance, right? L2 distance is parabola. So I put one memory here, and I put another memory here. So I get something like this, right, for the energy. Now, let's imagine I'm going to move these memories closer and closer together. At some point, what will happen, that they will stop being a local minima, and the whole thing will look like this. Right, so you will end up having a local minimum right in between, and like in your model, that would be the local minimum would be literally arithmetic average of the patterns, and that's precisely the point which corresponds to this bound. That's the point where.
Isn't the suggestion to have the distance to a single xi, which is the closest?
You can do that.
So it's not the sum, it's...
You can do that, but then the system becomes pretty much nearest neighbor attractor, right?
Yeah. Which is what so the system I described will not have the feature that you described, but I think it will be this nearest neighbor one.
Fantastic. If we do that, then it's a very interesting system. You would maximize the storage capacity. It would be big, right? Yeah. But the problem is it's not going to be a collective system. So if you need to choose between several of those, you're only going to pay attention to one closest neighbor. Yeah. And this system, if you kind of think about this class of models as a family of models, right? Depending on the function f, you can dynamically regulate that range, how far you're looking in terms of nearest neighbors.
Yeah. So I guess so maybe that leads to an actual question, which is there are some other desiderata, right? If I'm just interested in dynamics, which could be like steepest descent in geometry, arriving at a memory, then I can design all sorts of functions that have this property here.
Agreed.
And it's like, what are maybe I missed it earlier, but what exactly are the desiderata that are going into designing associative memory?
So the desiderata are the following. So one desideratum is that it's a neural network. Right, so like essentially, and I'm going to discuss this in a moment. You can write the minimization rule for this network as some kind of neural network update rule, and that has like some value because you can think about neural networks through the prism of this model. You can think about biological computation. So this is one desideratum. The second desideratum, the network must have error correction capabilities. So like what you're proposing, in some sense, you're proposing to pack a lot of delta functions in the n-dimensional space. And if you do that, you can pack a lot of them, of course, but it's not very useful because there is no error correction. If you're a little bit away from the delta function, you're done, right? So like that kind of capability should also be there. And even more broadly, in meaningful AI applications, we don't want to just pick between a couple of local minima. We actually want to organize those local minima in the form of manifolds and stuff. And that's essentially where these models begin to shine. And kind of, again, like your proposal would not quite work in that regime. But let me get to this. These are all very important questions, so thanks for asking. Yeah, indeed, like there are a few desiderata that are present here.
I guess you can think of this as being nearest neighbor as well, right? You're defining the distance to be this thing.
Yeah, exactly. If f is very steep, that's a nearest neighbor. That's one nearest neighbor.
Well, whatever you're doing, it is one nearest neighbor in this very custom-built distance.
Yeah.
Which is given by your dynamic system.
Correct. Yes.
Well, this is sum. If the sum were instead max or min, then it would be like nearest.
Then it would be like an L2 nearest neighbor, but it's still nearest neighbor by whatever that flow of that.
Yeah. So there is like a small cutoff on how much nearest neighbors we are including here. That is the correct intuition. Okay. So let me move on. So now, we played a little bit with these binary spins, right? Binary, neurons, if you wish. But of course, we want to do deep learning. We want to do transformers. We want to do some meaningful AI applications. For that, it's nice to have fully differentiable system. And it turns out that essentially the theory of dense associative memories can be directly translated to the domain when both the state vectors and in fact the time is a continuous variable. And it turns out that the right language for this is a language of ordinary nonlinear time-dependent differential equations. And also notice that I realize that this is not a neuroscience meeting, but in some sense, if you look at these kinds of equation, it has a meaningful biological interpretation if you would like to think about your axis as neurons. So then the xi would be the state of neuron I, and gi would be the firing rate of that neuron. So in that sense, again, we don't want to abandon that biological interpretation. We want to somehow play with some models that are both grounded in AI applications and in neuroscience applications. But to make a long story short, if you promote a binary vector sigma I, time-dependent vector, to a continuous vector and replace discrete updates with the differential equation, you can formulate dense associative memories. There is some nice theory with Lagrangian functions, with Legendre transforms that allows you to write Lyapunov functions and energy functions for a broad class of these kinds of equations. And people have worked out the memory storage capacity for many of these systems. And for certain choices of G, it can be super linear. And that is interesting. So essentially, pretty much like the simple intuition for the binary networks can be to some degree translated to continuous networks as well. So another remark that I want to make here is that, of course, the topic of Hopfield networks, it's preceding historically like convolutional neural networks, transformers, everything, right? And because of that, people often have this sort of cultural bias. Whenever you say, I work on Hopfield networks, people immediately think that you're doing some kind of, abstract mathematics that may have some, some intellectual value, but has nothing to do with practical applications. So I want to emphasize this very strongly, that the family of dense associative memories can have all kinds of inductive bias that we like in machine learning. They can, like the Hopfield layers can be convolutional. They can have pooling layers. These dense associative memories can have many hidden layers. And again, this network is a very different kind of network compared to what people mean when they draw a set of layers stacked from bottom to the top, because notice that here you have connections that go both ways. So the lower layers project to the higher layers, but also higher layers feed back onto the lower layers. So it's a fully recurrent network that evolves in time, right? It's a very, very different kind of network compared to feed-forward neural network. But what is interesting is that by now there is a theory developed for this class of models that incorporates all the known inductive biases that we like in machine learning. So in particular, you can have a convolutional dense associative memory, and that's just fine. So I also want to specifically comment on the attention, because attention, of course, and transformers in general is a very important class of Gen AI models, the workhorse behind pretty much all the LLM business. And this is the standard transformer block. And inside that block, arguably the most important part is this self-attention operation. So what people realized is that the self-attention operation is actually a very simple limiting case of dense associative memories. And what you need to do with dense associative memories to get attention is the following. So first of all, you need to do this sort of brutal thing. You need to terminate recurrence, right? So dense associative memory is an RNN. So first of all, you need to say, I'm going to start with some state, and I'm going to let this RNN compute for one step in time, and then I'm going to stop the computation. So of course, the network has not reached the local minimum yet, but you just don't care about this. You say, OK, I'm going to stop at that point, and I'm going to look at the update equation. So that's one thing that you need to do. And the second thing that you need to do, you need to pick a certain form for this function f. And it turns out that this function f should be such that its derivative is a softmax. So if that is the case, then essentially dense associative memory with, if you iterate it for only one step, becomes literally identical to the self-attention operation in transformers. So now the question is, like, when we talk about transformers, we have keys, we have queries, we have values, we don't have any memories. So where are memories, right? And it turns out the memories are actually keys in this framework. So the right way to think about this is the following. Think about a context window in an LLM. And let's say that you know n-1 previous tokens, and you're trying to predict the last token. So what you need to do is you need to take all the n-1 known tokens, and you need to multiply them by some matrix to produce some representation in the memory space. And then you should think about the state of the last token as the sigma in the previous slide, as the state of this Hopfield network. And essentially, that sigma needs to align itself with one of the keys produced by the previous tokens. And essentially, it needs to pick out of like n-1 tokens the most informative ones. And that's the kind of computation that is very natural for dense associative memories. So there is this idea, and on the one hand, it sort of allows us to think about transformers in a little bit more conceptual way. And what I think it's also kind of sociologically done to the field, it sort of emphasized this idea that the attention operation that historically has been introduced from the sort of signaling processing perspective, right? So like attention is all you need paper, it says that attention essentially is a convolution with large window and which is learnable. That's kind of like the paradigm that most AI researchers use for thinking about attention. So these correspondence open up a very different perspective on the attention operation. Specifically, it emphasizes that one can think about the attention operation as a form of working memory. So essentially what you do in the LLM, you take your tokens, you load them into your short-term working memory, and then transformer extracts it from that memory in a content addressable way and does something with it. And that's a very different kind of way of thinking about this computation. And it turns out that it's quite insightful for, in general, interpreting what transformers are doing. And I'll talk about this later on.
Can I just ask them, so you're saying the query is like the sigma, it's like the current state that the token produces.
Correct.
And the keys are the memories, and you're just sort of asking, well, how close am I to various previous?
Exactly.
And okay, then multi-heads is just many versions of this.
And multi-heads are many versions of dense associative memory, exactly, that work in parallel. So that's like roughly speaking the mapping. And again, like the keys are not raw tokens, right? So there is a raw token representation. Of course, the next word should not match, should not be identical to one of the previous words. So each of those previous words maps it into a different space, which is the space of, let's call it like how informative that word is for predicting the next one. And those representations become memories in this dense associative memory perspective. Okay, so one problem with this picture is that there are actually many problems. The first problem is that we first of all need to do this quite ugly thing. We need to break recurrence, right? We need to say that we're gonna only update dense associative memory for one step. And at that point, we have not reached the local minimum yet. So that's one thing that is somewhat unsatisfactory here. The second thing that is extremely unsatisfactory is that transformer is not just attention. There is all kinds of other stuff. There is feed-forward neural network. There is layer normalization. There are skip connections. There is a lot of operations inside this block that do not capture this, are not captured by the simple theory. And the question that I want to discuss next is, okay, if we think that this is the right way to think about transformers, can we actually design better transformers? Can we design transformers that would be fully recurrent and would incorporate all these missing elements, all these elements that people like to use in LLMs? And this...
Just a quick question. So, but in your point of view, right, there is no, it's just the attention block, there is no MLPs.
I'm about to introduce the MLP. Oh. Yes. So that's what I'm saying. In the previous point of view, there is no MLP, and that's unsatisfactory. And now I'm about to tell you how to introduce MLP, how to introduce layer normalization, how to introduce skip connections, how to make the whole thing recurrent.
comment on why one would want a recurrent transformer?
You mean from a practical perspective or theoretical perspective? Both. Okay. So from the theoretical perspective, I think it would be really wonderful if you could imagine that you can design an AI system that is, say, equally good to like state-of-the-art language models. But then you would also have some energy function that is being optimized in the inference time. And if you could have something like that, then you can reason about local minima in this energy function. What do they mean? You can think about things like alignment, right? For example, you could argue that some of the local minima might generate angry responses. Some of the local minima might generate polite responses. So how can we think about all of that? So from the theoretical perspective, I think it's an extremely desirable property to have. It's not just some kind of feed-forward computation that no one knows what it's doing. It's a black box. There's no clear interpretability. In contrast, you have an energy landscape. And that energy landscape has local minima. You can analyze the properties of those local minima. Are they like delta function-like? Are they continuous manifolds? What is the dimensionality of those manifolds? All these questions we can answer. We can try to answer them, right? Once we put the energy-based interpretation on top of that. So that's the theoretical perspective. From the practical perspective, I think it is also quite desirable. Think about it like this. Current transformers, they are big, right? So they have a lot of parameters. If you could perform the computation that they are doing not through stacking different layers, but through recurrently applying the same set of layers, then you can dramatically decrease the number of parameters that are used in your network. And essentially, like this energy transformer that I'm about to explain, it reduces the number of parameters that are used in conventional transformers by a factor of 20. Even more, factor of 50 in some applications. And that's, of course, a huge win even from the practical perspective if you, for example, want to run your LLMs on devices, right? I don't know, maybe your microwave needs to listen to you or something. Yeah.
Let's not talk about that.
Yeah. Okay. So let me talk. Let me introduce this architecture. We called it the energy transformer. And essentially, in one slide, the energy transformer is a model that is simultaneously three things. First of all, it is a transformer because it has self-attention, it has MLP, it has all the familiar blocks. It is also an energy-based model because I'm about to introduce the energy function, the global energy function that this energy transformer optimizes in inference time. And finally, it is an associative memory. And what I mean by that, it is a network with strong error correction capabilities. So essentially, if you give it some input and add some noise to it, it would be able to remove that noise. It is able of doing error correction. So I'm gonna work. I'm now going in slightly more technical details in the universe of vision transformers. You can do it for language as well, but for vision it's slightly easier. So in the vision transformer business, what people typically do is the following: they take an image and then first they tokenize it. They tokenize it in a very straightforward way. So they cut it in non-overlapping patches, and then they use a simple linear transformation to convert pixels into tokens. And essentially, if I take this kind of image, I will end up having 4 tokens. So then what people typically do, they add a little bit of positional embeddings to those tokens at the initial moment of time. And then that sum of the tokens plus positional embeddings is going to be passed to the energy transformer block. My energy transformer block is a recurrent network. So when I read out the output, it goes back into the input. So it operates and circles through the same set of weights. And I'm also going to define the energy function. And as the computation progresses, the energy function will decrease. And eventually, I'm hoping to get out of this something that looks like this kind of nice image, despite at the initial moment of time, I presented a corrupted image. Now, I want to emphasize up front here that this kind of problem setting is very different from my first slide. So you may think that here I have done something quite similar. The big difference is that here I knew the kind of images that I want to retrieve, right? I literally took some images and I encoded them. For the energy transformer, once it is trained, I want it to work on any kind of images. The images should come from the same distribution, but they should not be the same images that have been used in training. So this network should be able to generalize. Right. So let me now dive into the architectural structure of this block. So essentially, imagine that I have a collection of tokens X. And my variable X is going to have two indices. So index I is going to be a vector index. And that's a standard vector embedding for tokens. Index A is going to enumerate different tokens. Right? So think about A that runs from 1 to the size of the context window in LLM. So that's what A is doing. And essentially, I want to describe this energy transformer block as a gradient descent dynamics on a scalar energy function. And tau is some time constant. And the last thing that I need to define here is this new variable g. And the variable g is going to be a layer normalized version of x. So essentially, because layer normalization is a convex function, right? You can show that if your dynamical equation is given by this formula, then your dynamics minimizes E. So now let's take a look at what we put inside the energy transformer. So this is the conventional transformer 101. So it has the attention operation, it has feed-forward neural network, and it has skip connections and layer norms. So this is the energy transformer. And essentially, like this element, this module that we called multi-head energy attention, is an energy-based generalization or modification of the multi-head attention operation. So the dense associative memory is going to live right here inside this module. So the analog of the feed-forward MLP, or feed-forward network, we're going to call it the Hopfield network. And this Hopfield network is different from this Hopfield network. And I'm sorry for this overload of names, but indeed, it's unfortunately, it's hard to find a better one. So like the difference between these two Hopfield networks is that this Hopfield network is the dense associative memory. And this Hopfield network is the Hopfield network from the 1982 paper. So essentially, it's a very simple Hopfield network with quadratic F. And one big difference that you immediately can see here is that these two modules are plugged in parallel inside this energy transformer block, unlike the conventional transformer. And that's not unheard of. So if you look at various kinds of zoo of transformers and their modifications, people often do use this kind of architecture in state-of-the-art applications. So it's not really like something completely unheard of. The reason why we need to do that, because we want to write a differential equation. Right? And in the differential equation, if we want it to be a first-order differential equation, we kind of want to, to appear to something that appears on the right-hand side to be a function of x and g only. We don't want any, x's at previous time steps, right? So for that reason, we kind of have to plug them in parallel. Now, let's kind of, look a little bit deeper in terms of what the energy function is. So the energy function for the energy transformer is going to be a sum of two terms. The energy of the attention operation and this energy of this classical Hopfield network. And let's take a look first at the energy of the classical Hopfield network. So think about G's as the layer norm versions of the tokens X. And think about Xi's as memories. And again, if you kind of remember a little bit what I have shown you on the previous slide, this formula is very similar. So the analog of the function capital F of x is split here by this function capital G. But otherwise, it's exactly the same formula. So essentially, what I have done, I have, for every token A, I have written down a normal dense associative memory, or in the limiting case, a classical Hopfield network, and I have additively summed them up. So essentially, like this MLP thing, it does not mix tokens. So it operates on a per token basis. It's literally like takes the token and maps it into a different representation. The energy of attention, on the other hand, does mix tokens. And that's kind of what we want, because we want, like if we, for example, work with images, we want the information to be transferred from the tokens that we know what they are to the tokens that are occluded. So there needs to be some kind of mixing of the tokens. So the way this is done is described by this formula. So it's a little bit of a confusing formula, but essentially index h here refers to the number of heads. And let's imagine that it is not there. Let's say that we only have one head of attention. So then we have this index alpha that runs over internal dimension when you convolute queries and keys inside the softmax, which is also not particularly important. But essentially, what one needs to do is the following. One needs to compute the tensor Q, which is the tensor of queries, from the layer normalized version of the token X. And one needs to compute the keys. And the objective of this energy function is to align them. So essentially, you want, like that energy would be minimal if the state of the network is closely aligned with that representation that we discussed already before, that is produced by the previous tokens, right? And that's what this energy attention is trying to do. It's trying to align keys with the queries. On the other hand, the Hopfield network, this kind of Hopfield network, what it's trying to do, it is trying to align the state of the network with the parameters, with the memories. And by the way, these parameters of the memories would be the weight matrices inside the MLP. So it is trying to align it with some rows or columns, depending on how you write these matrices of those weights. And essentially, the whole dynamics of this energy transformer is the competition of these two desiderata. So one desideratum is trying to route the information from some tokens to the others, and the other one is trying to align the tokens, the occluded tokens, with some general representation of what a typical token might look like. So that's roughly speaking what the intuition is here.
So on training, which parts are being trained? So
right.
K, Q, the memories are trained?
Correct, correct. So first of all, XIs, right? XIs would be trained. So also, I should have written the definition of Ks and Qs, but essentially Ks and Qs are produced by taking G and multiplying them by WK and WQ. And those Ws would be learned. Right, so that's like pretty much like standard, KQV attention. So in the conventional KQV attention, there are these WK, WQ, and WV. So here, notice there is no WV, right? There is only WK and WQ. So we we got rid of that additional WV thing, and we'll figure out in a second where it appears. But these are the major parameters here. So essentially, it's WK, WQ, and XI. And there are a few more, because also the layer norm has some learnable weights. So those are trainable as well. And also, these vectors that we add for positional embeddings. So essentially, the way this is done, you literally look where in the image plane the patch is located. So for example, if it is located in the top right corner, you dedicate a certain position for that location, and you add it to every image, and you also learn those positional embeddings, right? So this is the complete set of parameters that are being learned here.
So how does G depends on X?
It's a layer norm. It's a layer norm. So essentially, let me just write it down. So essentially, GI is the following thing. It's so let me introduce xi mean, which is 1 over n sum over xj, right? So that's x bar, and then gi would be xi minus x bar divided by square root of the variance, sum over j, xj minus x bar squared. And there is a little bit of a small regularizer here. So that's a layer norm. And these parameters that I was referring to, typically what people do, they put a coefficient gamma here and a coefficient delta here. So essentially, like this delta I and this gamma would also be learnable. And for reasons that are somewhat technical, and I wish I had more time to explain this, in the conventional transformer, this parameter gamma would have a vector index. So you would put index I here. in the energy transformer that is prohibited because of the energy. So if you put gamma I here, you would not be able to find the global energy. So you need to restrict yourself to having a constant gamma. But still, it's a free parameter that you can learn. There is an MLP. So this is the MLP. Oops. So this is the MLP, right?
But that's a traditional Hopfield network.
Yes,
no? It's
right.
Not an MLP.
Yes, sorry, I'm going a little fast here, indeed. So let me explain this. So essentially, like this formula EHN, that's the thing that we like how we define it, right? So imagine you can see that it's additive in the token index, right? It's additive with respect to B. So let me forget about that sum just to make this argument more concise. So let's imagine that I only have one token. Then essentially, like the energy that you have here, it's sum over all the mu's from 1 to k. And this capital K would be the number of hidden neurons in the MLP layer. So essentially, conventional MLP in transformers looks like this. You have tokens, you map them in a expanding vector. Like typically in typical transformers, this is 4x expansion, right? You map it right here, and then you map it back to the vector of the same size, right? Let's call it n-dimensional vector, let's call it k-dimensional vector, and let's call this n-dimensional vector. And in the typical MLP, there will be a matrix W1 here, and there will be a matrix W2 here, right? And that would be what you would normally call an MLP. Now let's see how this thing appears from the Hopfield network. So the energy for the Hopfield network looks like this. It's minus sum over these guys, which are exactly the same hidden neurons. And here I'm going to write G of sum over I, xi mu I, gi. And again, I dropped index B because everything is additive in B. So because it's a linear derivative is a linear operation, we can do everything for one D. Now, notice that if I take the derivative of this, so this is a sum over I from 1 to n. So if I take the derivative of this function with respect to gi, right? And the reason why I'm doing this because I want to compute the right-hand side of this equation. So essentially what we would get is the following, that tau dxi dt is equal to something that comes from differentiating the energy attention that I'm not going to write. But then I'm going to write this piece. And this piece is going to look like this. It's going to be sum over mu from 1 to k, xi mu I, g prime, sum over j from 1 to n, xi mu j, g j. Right? So I just literally took the derivative of this thing, and prime is the derivative. Now, let's imagine the following. Let's call this xi W1, right? Let's call this g prime the activation function that lives here. So this is the activation function g prime of x. And let's call this other xi W2. So essentially, you can see that what I'm using here is nothing but MLP, but when W1 and W2 are shared. So essentially, W1 needs to be transpose of W2. And that W1 and equal to W2 transpose would be equal to the Hopfield memories size. So that's literally like all that I have done. I have moved the MLP that follows the attention. I have moved it in parallel, and I have shared the weights within that MLP. And that's what the Hopfield network is, essentially. Right?
And your algorithm will be effectively the same, you're saying, as training an MLP.
So I have not talked about training yet. So let me briefly comment on that. So everything that I'm discussing here is inference, right? So like here, somehow imagine that we have trained already networks. Someone had given us all the x's, all the w's, we know them. And then what I'm saying is that when the weights are fixed at inference time, like that my system is doing gradient descent on the energy landscape. Now, you're asking, okay, but how do I get those W's to begin with? So you would do it in the following way. And that's one possible way. There are others. But in this system, it is done in the following way. So you start with this kind of image, right? You take an image from the data set, you patchify it, then you occlude some pixels. Then you run the inference path through the transformer. You iterate it through, say, 12 steps. Then it produces something. And it's not going to be as nice as this parrot. It's going to be some kind of mess. So you take that mass and you subtract it from the ground truth, and you make an L2 distance. And that's another function, we call it a loss function, as everyone else, right? And then you optimize that loss function with respect to W's. So that's how this network is trained. So essentially, it's trained with backprop, and it's kind of like alternating minimization, if you wish, because in the inference path, this network is minimizing the energy. And in the training path, it is minimizing the loss. And the energy is minimized with respect to the token states, and the loss is minimized with respect to the weights. Right?
So at the beginning, when you pointed out that multi-head could look like the gradient of your modern Hopfield, I thought you were going to do was you would take the standard transformer block and say, let's just adopt this as our gradient, and then ask what is the energy function it corresponds to.
The problem is that the standard transformer block is not a gradient field.
Okay.
Right? Yeah. And essentially, you're right that essentially what we're trying to do here is to modify it, to do a minimal modification to the standard transformer block so that it becomes a gradient field.
Okay. Okay. So that's the guiding principle here.
That's the guiding principle, okay. Indeed. So hopefully you kind of convinced that, this is a reasonable transformer, right? It's not exactly transformer because it's a gradient field, because transformer is not. And again, kind of, what makes it a gradient field? Like, for example, here, if you assume that W1 and W2 are different matrices, it will not be a gradient field. You need to share them, right? You need to do a lot of like these little modifications to make sure that like your block is actually a gradient field.
And I guess, so now, thinking a bit more, what's the advantage of having gradient fields? So then I guess I can immediately understand what the dynamics are going to be after repeated application. It's going to be percent.
Yeah.
Now, in general, I can still ask about long-term behavior. Would be a Markov chain, say, after repeated application, and there are, so. I guess maybe this goes back to the higher level question of why should we seek architectures where the blocks are correspond to gradient fields,
right?
Versus say Markov chains with well-defined stationary behavior.
You could do that. You could do that, and I think if the second paradigm leads to a broader class of models, that could be valuable, right? But indeed, kind of, I mean, in some sense, it's also somewhat of a question of like which field you're coming from, right? And I'm a physicist, and for me, kind of, it's very intuitive to have energies, to have particles that talk to each other, that interact, and that's that's kind of like the intuition where this system comes from. So, but I mean, I'm happy. I would love to hear your perspective. If you see a different way of conceptualizing this, I think it might be super interesting.
You know that one of the advantages over pathfinders would be number of parameters. What about training time and also interoperability of the learned representation?
Wonderful question. And the good news is that my next slide is right about that. So, but let me answer your question like briefly, and then I'll elaborate more. So essentially, in terms of number of parameters, we already discussed this. I think you agree that indeed we get a win. And again, I sort of emphasize that we recurrence as a means to save the number of parameters. But also notice that this weight sharing that I have explained here, it's a huge win in terms of the number of parameters because this vector, it's a very, very broad vector. It's a very kind of long vector, and because it's a all-to-all matrix, it's a dense matrix, right? Essentially, all the parameters in transformers they actually live inside the MLP, And by reducing the MLP to the Hopfield network, you essentially cut it in half. Right? So that's a big win. It's not just, you divide the total number of parameters by the number of layers. You actually take the biggest reservoir of those parameters and you decrease it further. So yes, that's one thing. In terms of training, it's approximately the same number of flops. So essentially, like if you take the derivative of this energy attention, it would have the normal piece and it would have a little bit of an extra piece. And that extra piece, you also need to compute it. But the thing is, the overhead is just a constant factor. So you would have a little bit more flops that you need to do. But that extra addition would not scale with whatever size you have. So it would be just a constant number. So we can probably live with that. Now, on the interpretability front, there's a huge win of the energy transformer, and I'm about to explain this. So first of all, let me, by the way, say that this is not just some kind of abstract mathematics. It actually works, and let me show you some examples. So here, this is the ground truth images, and these are novel images. They have not been used in training. They're taken from a different set, right? So this is the initial state that is given to the energy transformer. And I'm going to play this movie, and you can pay attention to what is happening in the middle column here and here. And so essentially, the dynamics here is unfolded for 12 time steps. After the movie reaches the 12th step, it jumps back to the first step. So that's why you can see some discontinuities at the end. But hopefully you would agree with me that it works very nicely. For images that it has never seen before, it's a really meaningful, meaningful understanding, in quotes, of the space of natural images. So for example, if you pay attention to this boundary between the green background and the fur of this dog, you can see that it's almost entirely occluded, but it is being reconstructed very nicely. So indeed, kind of like the network has learned some meaningful rules about how tokens are glued together to form a properly looking image. There are some funny things. You can, like, for example, take a look here, and you can see that there are no boundaries on this brick. It's a very long brick, which is very different from the ground truth. Oh, okay. Then let me move on. So, do you want to hear about interpretability or diffusion? Okay, let me skip interpretability, and we can discuss. But just to make a long story short, energy transformer is extremely more interpretable, much more interpretable than the conventional transformer. And the reason is that whatever computation you are doing, you are only one decoder step away from the image plane. So essentially, every time you see a vector index inside anything, inside activation weight of the energy transformer, you can take that vector index, this index I that appears everywhere. You can act on that vector by the decoder, and you can see what it means in the image plane. And that means you can literally like see how much computation is done by the attention versus by the MLP. You can see what attention is doing early in the unfolding dynamics versus what it does later in the unfolding dynamics. Right. So it's a very kind of interpretable system from that perspective. Okay, let me skip this. I want to briefly make some statements about diffusion, because of course diffusion is another huge paradigm in Gen AI these days, right? Like these kinds of amazing images that you can produce from prompts with photographic resolution that are, completely unthinkable of being real, but state-of-the-art diffusion models can do that. And the question is, can dense associative memory somehow help us understand what these models are doing? And essentially, like my second half of this talk, which was supposed to be half an hour, sorry about that, bad planning on my part, was about to convince you that indeed they provide a very nice framework for thinking about diffusion models. So let me kind of at the high level explain to you what I mean by that. So when we do diffusion, we do something roughly speaking, the following thing. So we take some y that comes from a data distribution. Y is a vector. Think about y as an image. And then we add noise to it. And for the sake of the argument, I'm going to work in a variance exploding paradigm of diffusion. Sometimes people kind of use variance preserving thing, and that one is a little more complicated, but the final result is the same. So in the variance exploding framework, what you need to do is you need to convolve that initial state with the diffusion kernel, with an n-dimensional diffusion kernel. Now, imagine that I don't know the true distribution of my data. I don't know P of y. But I have my data set, and I'm going to write an empirical distribution. So essentially, my xi mu's would become individual data points from the training set. So if I do that, I can rewrite the probability of the noise data, once we already have added enough noise to the data, in the following form. So now let me define a new quantity. I'm going to call it energy of the diffusion model. So energy of the diffusion model, modular prefactor, is going to be just a logarithm of that probability. And if we just literally use this definition, we can see that this logarithm of this probability is given by this expression, where xi mu are my data points. And interestingly, this formula is nothing but one of the frequently studied models from the dense associative memory family. So I have written this energy function for this model right here. And essentially, xi mu's would be memories, and x would be the state of that dense associative memory. And again, kind of, already starting from my first slides, you could see that there is a lot of similarities between associative memories and diffusion, because in some sense, the reverse pass in diffusion, it's denoising step, right? And this is just a little bit of a rigorous formalization of this idea. But notice that something quite interesting happens here. So the parameter beta that people use to define the energy of dense associative memories, which corresponds to the inverse temperature, now becomes time-dependent, right? So it's a very different kind of way of using dense associative memories, because typically in the dense associative memory literature, beta is constant, and here it's time-dependent. But if we go back in time, and that's what we do in the reverse pass, beta becomes bigger and bigger and bigger. So essentially, we are going from the regime when we have a little bit like a classical Hopfield network in the limit of large times, to the regime when we have this modern Hopfield or dense associative memory in the limit of small times. And that's essentially the intuition behind the correspondence between diffusion models and dense associative memories. Now, the question is this just some kind of, again, funny intuition, or can we actually do something meaningful with this? And I have a whole talk dedicated to explaining to you that we can. And in fact, if we study what people in the diffusion literature call generalization to memorization transition, it's literally the story about the memory storage capacity of dense associative memories. You can literally take that theory and literally apply it to the diffusion models. And you can identify all the intermediate states that kind of arise in this transition once you go through the critical memory storage capacity in dense associative memories. So in particular, I'll just give one example. There is a very well kind of defined notion of so-called spurious states in the associative memory models. And in the diffusion literature, there is no such a word as spurious state. It's not an existing concept. So it turns out that you can define it, and you can take state-of-the-art diffusion models, and you can find those spurious states there. And those predictions, they kind of literally come from the dense associative memory theory. You would not be able to make those predictions unless you adopt this energy-based perspective. So I kind of with that a little maybe confusing statements, I'm gonna just jump to my conclusions. So as a conclusion, I want to say several things. First of all, dense associative memories indeed have much nicer computational properties than Hopfield networks that people used to play with back in the days. And again, both binary and continuous. So by now there is all kinds of there's a developed theory for both frameworks. So Hopfield networks can have, these dense new modifications of Hopfield networks can have all kinds of interesting inductive biases. Attention, convolution, layer normalization, this is all follows from a nice theory, and you can compute energy functions for all those layers. Also, I believe that dense associative memories provide a very interesting perspective on diffusion models. And that's like a very sort of emerging topics. It hasn't been sort of it hasn't been fully developed yet, but I think there are a lot of exciting links that one can explore on that front.
Thank you.